So today we're going to do a bit more on dimensionality reduction. So we sort of talked a bit about linear PCA last time, but the thing that I sort of want to make clear is this technique it's like the culmination of multiple different approaches, different ideas about how you might visualize data. Now, principal component analysis is first described in the form that I think we should call it principal component analysis by Hotelling in 1933. And Hotelling is actually responding to papers from factor analysis from the early, I guess, psychology literature, which is very eugenics oriented. And he's sort of saying, well, the notion of a factor is the wrong way of looking at this because factor has a mathematical meaning. So he prefers to use the word component. But the way it's mostly presented today is not the way Hotelling develops it. Hotelling develops it in a as a latent variable model, which we'll review in a second. But often the way it's presented is by finding directions of maximum variance. And it's credited to Pearson from 1901. And the reason is because it turns out that both directions of maximum variance and the latent variable model are solved by the same eigenvalue problem. And so you might think, well, that means they're the same thing. Well, yes, they are the same thing in the linear case. But the interesting thing is when you non-linearize these different models, they go in different directions. So if you try and take the same concepts to a non-linear world, so you try and find curves of maximum variance, if you define that in a particular way, or you define non-linear latent variable models, you get totally different algorithms. So in some sense, while it seems a bit philosophical to sort of talk about these different things which lead to the same algorithm, it's also important for deeper understanding of other dimensionality reduction methods, which we're not going to go into here. But I do think the distinction's interesting. So originally, as I say, it's Hotelling, and it's a linear embedding, but today it's presented as rotate to find directions in data with maximal variance. So how do we find these directions? Well, what we do is we look for a matrix U, which is sort of orthonormal matrix, which when projected onto Y, the data points, finds a direction in which these things are maximized. I think I'll go forward to my diagram actually first. So what does that look like here? Well, hopefully if my diagram's working. Oh. Right, so this is a sort of data. And I generated this data from a highly correlated Gaussian, right? With zero mean and sort of strong correlation. And this ellipse represents the contour of that Gaussian that sits at, I think, 2 standard deviations. So normally when we look at Gaussians, we're seeing them from the side. Here we're looking from above and seeing one contour. And the data's coming from there, and you can sort of see, oh, some of this data's, actually, it's probably must be 1 standard deviation, looking at the fact that the data sits mostly outside it. But then what do we do when PCA? Well, if we think about this space, find an arrow, a pointing arrow, where when we project the data down onto that pointing arrow, the variance will be maximum. And then that pointing arrow turns out to be not that direction, this direction. So that's the orthogonal direction to it. But this direction, or equally, we could choose that direction. It would give you the same maths. There's a reflection on there. And these turn out to be the eigenvectors multiplied by the square root of the eigenvalues of the covariance matrix. So what's going on? Do people recall like the form of a multivariate Gaussian? Or should I write that up? I can write that up. Let's see. F screen, right visualizer. Yes. Okay, so a Gaussian in 1 dimension with zero mean one standard deviation is drawn like that and is of the form sort of 1 over 2 pi square rooted exponential of x squared over 2 sigma squared, where this is a zero mean. I could subtract off the mean. But in this case, I've just put a mean of 0, and the variance could be this, that standard deviation I've marked here, so that's sigma. Now, in higher dimensions, what happens is you can actually just multiply these things in 2 dimensions, right? So you can actually sort of say, well, what would it be if I wanted across x and y? Well, if I take 2 of these together, so I get 1 over 2 pi to the half times 1 over 2 pi to the half, because that's coming twice. Exponential of minus x squared over 2 sigma squared. Now, if I'm defining this in y, so I'm sort of somehow doing an x, y Gaussian like this, then if I multiply by exponential of minus y squared over 2 sigma squared, but let's call them now sigma x and sigma y, then that's going to give me a sum in the exponential. So then I just get O minus y squared over 2 sigma y squared, x squared, y squared, like that. Yeah? And that product of Gaussians, if I now draw that in 2 dimensions, what that looks like, it looks like a sort of Gaussian sausage where that sigma is sigma x and that sigma is sigma y. Okay? So these are independent because it's P of x times P of y, right? So this is P of x, and this is P of, that bit was coming from P of y. But the joint distribution is P of x, comma y. So there's no correlation here, right? And I can actually rewrite this in the following way. I can rewrite this as minus x, y times sigma x, sigma y squared times, let's transpose, times x, y, in a little matrix form, yeah? And we typically call that thing sigma. Now, imagine that I want to introduce correlation. Well, what we just saw on the plot before was a rotated form of this, wasn't it? It looked like that, yeah? So if you rotate the axes in this case, so if I'm rotating both x and y, if I put a rotation in, so I'm missing the sigma down here, sigma squared, sigma squared. If I'm putting the rotations in here, so a rotation matrix and a rotation matrix, well, in fact, why don't we just call that U and U? So it's an orthonormal matrix. Then that rotates the axes, right? It doesn't actually change what's going on down here, but this rotates the axes here. And this object here, I can then, so what I'm now saying is I've got x, y, u transpose sigma x squared, sigma y squared, and then times u times x, y, to rotate these 2 axes, right? So this is a rotation of this space because this is an orthonormal matrix. But now if I look at that thing, I can rewrite that as U transpose, and I'm going to call this thing lambda U. And that turns out to be a positive definite matrix, which we typically call sigma, the covariance matrix. So the covariance matrix is made up of 3 components: a rotation axis, a diagonal, and another U, which is so rotating it back the other way. If we, in effect, it's got a square root of something which is like U to the sigma half. Now, why do I mention that? Well, going back to what's on this side, that's exactly what's being visualized. The U is a 2 by 2 matrix that has 2 vectors associated with it, scaled now by lambda 1 and lambda 2, right? And so what you're doing is you're seeing the axis of scaling and rotation that takes you from this thing back to a standard normal of zero mean. So that the operations you're effectively applying are first a scale, which is the standard deviation coming from the square root of lambda, and then a rotation. And that's what's giving you a multivariate Gaussian. And this works in all dimensions, right? So when you're looking at the principal components of a data set, what you're actually looking at is the decomposition or diagonalization. I mean, it's a diagonalization technique, but what it actually means in terms of the geometry of what's going on in probability space is you're sort of decomposing, you're normalizing your data in such a way that if you were to apply that rotation, it would become axis aligned, i.e. uncorrelated. And then if you were to scale it, then it would become variance 1 in both directions. Does that make sense? So, and that's how some people view PCA. Now, what actually the question Pearson was interested in when he came up with this algorithm was he noticed, imagine that this is a regression problem instead of a dimensionality reduction problem. Imagine across this lower axis, we've got some input X and output Y. Well, he noticed that if you do regression where your input is X and your output is Y, you get a different answer for the coefficients than if you do a regression where your input is Y and your output is X, right? That's true. The lines aren't quite the same as this line that we're getting here. They're slightly different. So he noticed that and said, well, I want a method that makes it the same in both directions. And this is what he came up with. And then he showed that it's finding the directions of maximum variance in the data. So not actually really to do with what we're going to see Hotelling was trying to do in a moment, but the algorithmic solution of diagonalizing the covariance matrix, which I tried to just give you the intuition of geometrically, turns out to be exactly the same. And that's funny because there are other approaches we'll not talk about today, which are the same. So there's a sort of last year, Carl-Henrik went through multidimensional scaling, which is where you're trying to match distances in the latent space to distances in the data space, or squared distances. And you're trying to do this matching through a linear projection. And the answer turns out to be, oh, diagonalize the covariance again. So this thing comes up again and again and again. It doesn't mean like it's the most general method or the most powerful method, but it means under these very simple assumptions, it's quite a powerful method. It's quite a general method. So seeking these directions of maximum variance, what we do is actually we solve this through, and this is the way you'll find it described in many textbooks. You solve this through an eigenvalue problem. So what you're doing here is this is the covariance matrix, and you can do a bit of linear algebra to show that the first vector of that orthonormal matrix I'm talking about multiplied by the empirical covariance matrix, so we don't know the actual covariance matrix, so we just measure the covariance, gives us the product of these two gives us the variance. And so you're trying to maximize this thing. But what you do is you want to maximize it with the constraint. Obviously, if you don't have a constraint on the length of u, you could just maximize the length of u, and then everything would scale up, right? So you then put a constraint on it that says, well, this is a Lagrange multiplier constraint that says the length of u is 1. So it's a normal vector, right? And then if you solve that, you end up with this little equation here. That gives you the first eigenvector, which is, if you look at this solution here, the solution is going to be that SU is equal to lambda 1U1, which is the definition of an eigenvector. So the solutions are always eigenvectors. And then the next thing, when you do the second one, you have to add an additional constraint that it should be orthonormal to the first. So when you see this thing going on here, this is the second one. It's the direction of largest variance, which is orthogonal to the first. Well, in fact, it's just orthogonal to the first because there's only two directions here, right? But in higher dimensions, that's what it would be, right? In this case here, once you've done the first, the second is the residual variance in the remaining direction. And that's kind of one way of thinking about the eigenvalue problem. But rather remarkably, there is this other approach that is the Hotelling approach that I find much, much more interesting in relation to what we're trying to do. So what we're going to do here is represent data Y with a lower dimensional data set of latent variables Z. And we're going to be explicit about what that representation is. So we're saying that every observation Y, so Yi is the ith data point, and it's the row of a sort of, let's try and get that right screen, right visualizer, nice. What this is saying is that our data is being presented to us in a form like this. So every data point is yi comma colon, y1 comma colon, down to yn colon, right? Like that, yeah? So that's the form of our data matrix there. And what we're saying here is, well, we believe this data to be generated from some unknown z, a z that we don't see, which is actually going to be lower dimensionality. So this dimensionality typically be P, or in P in statistics, or in machine learning, it would be called D. And then the lower dimensionality we would call Q. And then that's going to be Z, sorry, not X, Z1 to Zn. A series of unknown latent variables that we don't see that are causing this thing, right? And then what we're saying is that there's a linear projection between these two. So in other words, Z is approximately, sorry, Y is approximately equal to W times Z, right? That's what this thing is saying here, with the approximately being the some corrupting noise that we're saying is sampled from a Gaussian. So Y is high dimensional, W is a matrix, which is going to be P by Q, or in machine learning terms, it would be D by Q. And sigma is going to be a P or D dimensional, depending on whether we're using machine learning notation or not, vector. Now, sometimes we would draw this as a graphical model in this way, and apologies, I flipped X for Z here. We would draw this as a graphical model in this way. What we're saying is that there's some latent variable Z that is causing, well, is through this projection W is turning into some observed variable Y. And what we're interested in is visualizing in this space here. By plotting these Zs, we're going to visualize. Now, if we do the maths, and the maths turns out to be remarkably straightforward, because we could just use properties of multidimensional Gaussians to show that this means the following thing. So if you don't know if you remember your sort of Gaussian properties, but there's things like the sum of two Gaussian random variables. If you've got x1 plus z1, and they're both Gaussian distributed, then there's this remarkable property, which doesn't seem remarkable the first time you see it, because you think, well, they're just adding, is the variance. If this is drawn from a Gaussian with zero mean and variance sigma x, and this is drawn from a Gaussian with zero mean and sigma z squared, then the variance of the result, we call that y, is going to be drawn from a Gaussian with zero mean sigma x squared plus sigma z. And the fact that it stays Gaussian is remarkable. I mean, that's the weird thing. You don't get emphasized that enough, because every other thing, when you do this to it, tends towards Gaussian. That's the central limit theorem. So if I do this with non-Gaussian variables, they don't stay in the form they started in. They become Gaussian over time. So this remarkable property means that when we're adding variables, and if we were to put a mean in here, mu x and mu z, the means would just add mu x plus mu z. It means when we do linear algebra on these things, which is just simply adding and scaling, there are really simple linear algebraic properties. So if we take a Gaussian, something from Z, which is drawn from a Gaussian with some mean and some covariance C, and then we say that Y is equal to WZ, we immediately know that Y is drawn from a Gaussian with mean W times the mean of the first one, which in this case would be 0, and covariance WC, W transpose. And that rule is the simple way, that's how we're getting this result, right? Because what we're saying in this case is these latent variables are 0 mean and unit covariance. So it's not quite, I'll call this F is equal to that. And then we're corrupting it with Gaussian noise. So F plus sigma, where sigma is drawn from a Gaussian with zero mean and covariance sigma squared I, gives us a sigma squared I in here. And that's what you're seeing here. Yeah? Now, this is a probability distribution with a particular structure of covariance. And it's a really interesting structure because what you have here is a low rank form, right? This is a low rank form, and this is a spherical term. So in order, if it were purely the low rank form, then this wouldn't be a valid probability distribution because you couldn't compute the determinant of the covariance matrix. The determinant is 0. So it would be a sort of, the equivalent of a delta function is a very difficult distribution to deal with. And that's effectively what the low rank thing is implying, that in some directions, there's 0 variance, right? Which is not something that you can use. But in this form here, we've got this low rank form WW transpose plus sigma squared I. And this form, it turns out if we fit this, the maximum likelihood solution for W, if we decompose W in this way here, turns out to be, again, the eigen decomposition of the covariance matrix. Yeah? Or in particular, the case Hertelling looked at was where sigma squared goes to 0. So he looked in the limit. It's not a valid distribution, but he took the limit as sigma squared goes to 0. And when he did that, he found, oh, this is just the eigen decomposition of the covariance matrix, right? So although these sound like two very different things, they turn out to lead to the same algorithm, which is principal component analysis in both cases. Okay, so I think we probably covered that. So I think I'm trying to teach you that just to give you the intuition behind what's going on with principal component analysis. But in some sense, you know, the application of it as a visualization technique, what we'll see is you don't really believe in this model. You don't really believe there's some latent thing that's drawn from a Gaussian like that is being twisted out, right? That would be very unstructured data. And you rarely see that when you project back to latent space, some sort of Gaussian blob. So the model is typically wrong, but it's still a useful way of visualizing. So this is the oil data we looked at with the hierarchical clustering last time, where these 3 different classes are representing these different flows of oil in a pipeline that are being measured in 12 dimensions. And what we're doing here is I've just, in the notes, if you want to go through the notes, I've derived PCA, I've given you the NumPy implementation, I've shown you how to do it stably in NumPy, but then I'm basically saying, just do it in scikit-learn, right? Because that's someone else has done all that for you. But just to give you the sense of what's going on here. And so this example in the notes is a scikit-learn example. Oh, somehow I've missed that. Well, I better go to the notes. I wonder if that was going to happen. So this is all that material talking about, yeah, sorry, these blocks, I need to fix that. They're ends for normal distribution. I'm not sure why they don't render in MathJax. Not math, what's it called, the online thing? So there's some playing around here you can do. If this is not assessed, this is just stuff if you're interested. And this is the description of how you solve this system. You find the eigen decomposition that I've just been through. And then we're down to this sort of implementation here. Let's see. Oh, okay. So let's run these. I think I can just run from scikit-learn implementation. Oh, it will want me to install pods, won't it? That's done at the top. That's just getting the data in a nice way where I can show the labels. It's just some processing of the data. Not very interesting. But down here is the sort of the main bit. Here, we're first of all plotting the data according to its labels. That's going to ask me about downloading this data in a second. Wow, there we go. Oh. Again, that's done at the top. So it should be okay if you run the whole notebook. So this is just for that plot there, right? So that's just taking the data and a couple of two dimensions of the data. We could play with that if we like, and plot maybe the first versus the third dimension, and you will get a different plot. Yeah. So that's another way of visualizing data. We do that in the first review and refresh lab. And now here, oh, so it won't like that. It will want scikit. Installing scikit-learn and just importing PCA from scikit-learn. So look, it's very simple, right? It's just saying here, extract two components. Oh, it's got the scikit-learn installed, nice. Extract two components from the data. Oh, somehow I've lost this. Oh. And then, yeah. Let's transform. It did that. Oh, thank you. Yeah, I can't see it from this angle, even though it was pink. And then we can now do a scatter plot of the first principal component against the second. And all I'm doing in this scatter plot, the Y here, which I think should be a capital Y, is the label, right, of the data as defined above. So that's going around 3 times to just plot each. To plot each of these labels separately. Okay, so that's all why there's a loop there. If you were to just plot like this, oh. What have I done there? Wrong bracket, is it? This angle's very hard. Like that. Too clever by half these things. There you go. Oh, what have I done there? Must be a scalar or a float. Oh, I'm just going to copy this one. Oh, no. Hey, what have I done there? So it's saying must be a scalar. Same size as X and A. Anyone spot it? Yeah, I thought you shouldn't. Ah, no, it might be it might just not like that might be a bit MATLAB-y of me. Old habits die hard. Where did it go? Oh, because I haven't got an axis, do I? There we go. Yeah. So Only took half an hour to do the simple thing there. I'm doing it like this. Probably the whole time, like Gemini was telling me, do this, but I couldn't see what it was saying. Right, so yeah, and that's a nice thing to do. Like if you do have these sort of labels, this is a key thing in visualization. If you know aspects about your data, plotting them in such a way is sort of helpful to see what's going on. What you're sort of seeing here is that these regimes seem to be separating quite well from these other two regimes, but these other two regimes seem to be overlapping. The regimes in this case are like homogeneous flow, laminar flow, and annular flow in the oil pipeline, right? And that's what they're labeled with. Let's try doing a third component and then trying to get, so because it's always sometimes worth plotting an additional component. Oh, that. So we'll try doing a third component and we'll look down the direction of the third component. Yeah, there you go. So again, it doesn't seem that the third component has separated, but you can also look at component one, right? So maybe there's a little bit more separation there. I don't know. I think if we go to, if you go back to, I think those of you who managed to do the first review and refresh, you'll see in here this type of plot, right? You remember doing that? So you can actually do these plots for principal components as well. So you can say each principal component and do all the plots and then visualize your data in that way. And then you get a sense of how well it's separating. So I had a very interesting case of this where someone who I know quite well was applying to a company, right? And they had to do a coding test for this company. And this company was a pharmaceutical company. And they told them, oh, before you do your coding test, well, they said, for your coding test, we want you to download this cancer data, this genomic cancer data. And then we want you to apply a variational autoencoder to visualize the cancer data. And then we want you to apply a deep neural network to classify it. And this person was a very well-trained bioinformatician. And okay, they knew about deep learning, but they weren't quite sure how to use. And I said, just do the analysis as you would normally do it. Ignore the instructions for the moment. It could be a trick. And so this person, what she did is she did, as she would normally do it, and she did PCA on the data. And immediately, the cancer data separated cleanly in the first two principal components, right? So the whole thing she was being asked to do was a waste of time, because actually you don't need a variational autoencoder because the data separated. And then what she did an L1 classification to separate the data and extract genes. And then she submitted that. And then just to be safe, she went and did the neural network stuff. But the funniest thing about that coding test is the people that set the coding tests didn't realize that the data was linearly separable. And so someone at a big pharmaceutical company was telling her that the right way to analyze data was with a variational autoencoder, when in that data's case, just like what we're seeing between these regimes, not between the blue and orange regimes, but you were getting as good a separation as you're getting perhaps between this green and the orange and blue in that data. And this is going on all the time. I mean, this is a major company that was setting a coding test for someone, making them do an overly complex method of visualization that would actually be probably beyond the compute resource that most individuals have available, when underlying it, that the data is linearly separable. And so the funny thing, when you're looking at this, you're simultaneously, if we go back to the first and second principal component, you're actually looking immediately at a few different things. You're looking at the direction of highest variance in the data, which is being determined by the fact that one of these clusters is a long way away from the other, right? So that's what's dominating that direction of high variance. And that's something that happens in PCA. If you do have outliers, they will dominate that first dimension. And one of the things that often happens when you first analyze the data set, if you haven't looked at it carefully, is you might find, I mean, I'm not sure to what extent people do this anymore, but in the past, people used to encode outliers with crazy numbers, not outliers, missing values, like -9999. They didn't put a nan in. And so the first thing you would see in the first principal component is the data which has missing values all streaming up in one direction. The more missing values, the larger the values are, because you're looking at the directions of maximum variance, right? But simultaneously, you're also looking at a linear projection of this data. The best linear projection, so we can show PCA, is the optimal linear reconstruction of the data under linear projection down and linear projection back up. This is optimal. So you're seeing the best linear reconstruction in the least squares sense as well, which is also interesting. And you're seeing these things at the same time. The other example I then show is a different data set. It's a motion capture data set. And this motion capture data set, I'm interested in showing because it's a sort of person running like this, and it's 3 strides of running. And what you're seeing in the motion capture data set is that the 3 strides of running line up. So this is like the loops of the pace, right, going around and around. And these things here are all lined up in the same direction. Now, in both cases, notice you're not seeing a Gaussian blob, right? You're not seeing like a Gaussian blob in the latent space. So our model is wrong, but you are getting to see the structure in the data because you're looking through a linear projection. I mean, what we can immediately see here is that this is some form of cylindrical structure. This is the start of the run, where the pose of the run is in a slightly different position. So you're immediately getting these instincts for the data, even though the model isn't quite right. Okay. So we'll just go on to do some bit of stuff on going beyond these linear methods, because, yeah, in practice, things aren't often linear. Well, neither of those things was linear, right? So, I mean, it's interesting. The notion of dimensionality reduction failing is sort of a lot dependent on the context. Why are you doing the dimensionality reduction? It's not failed to do PCA if it's taught you something about your underlying data set. But if you're then thinking that this is a good model of the data, if you try and generate from that model, like in the Gen AI sense, you won't get very impressive results. But there are data sets with highly nonlinear relationships between dimensions. And a classic, I mean, almost to a ridiculous extent, one example of this has been the Swiss roll example. So this is data people have used to demonstrate. I mean, this data never exists like this in practice, but somehow it became a big data set for people to talk about. So this data set is like a Swiss roll going around like this. And in about the 2000s, early 2000s, there was like a cluster of methods people were using on the Swiss roll data to try and demonstrate we can do nonlinear dimensionality reduction. Class of methods I'm not going to talk about much, called spectral methods, with names like isomap and locally linear embedding. And they pretty much all worked by, first of all, building a graph structure that interconnected the data points. So you look for nearest neighbors. So these points here would be a cluster. These points here would be a cluster. And then you build the graph in such a way that you're hoping you don't get a shortcut going from one point to another point in the manifold. So this Swiss roll structure, if you can see it, is kind of like this, right? And then it's linear in that direction. So it's like a Swiss roll, which I don't know if you know. I mean, it's the sort of thing I used to eat as a child in the 1970s. I don't know if children eat it nowadays. Probably very unhealthy. But probably wrong also to call it a Swiss roll for some reason. I don't quite know. But anyway, the problem can be if the graph jumps across, that messes up those methods, because the graph structure is what is actually capturing. And in effect, all those methods are doing some form of replacing distances in Euclidean space with distances along the graph. So those are sort of spectral methods that are used in that case. And then very commonly used is these 2 sets of methods, UMAP and t-SNE. So t-SNE is really, it makes amazing visualizations, but when you see the description of the method, it's sort of totally not clear why. So one of my PhD students, Aditya Ravuri, is actively working on trying to better explain why t-SNE works. But the original motivation, which I've talked about in detail in the notes, is this very weird thing of building neighborhood structures in data space, building neighborhood structures in latent space, putting probability distributions over those neighborhood structures, and minimizing an information theoretic measure known as the KL divergence between them. It's sort of, if you know about these things, it's, oh, that's an interesting thing to do, but it's sort of not clear. It's so much harder to describe in terms of what we just had on that side, which I just switched off in that moment, in terms of like a manifold method. But it really creates some very cool visualizations. And here's one for the oil data, right? So it's got a parameter called the perplexity. The perplexity is like the neighborhood size, right? How big is the neighborhood? Because it has this notion of neighborhood in it. But look, it's separated everything, right, in 2 dimensions. And this perplexity here, to me, seems the most suitable, because actually in this perplexity, you're seeing that there's approximately 3 clusters from the red, a big cluster of the green, and then these were the things, those ones on the outside. I'm afraid the colors have switched a bit from the previous one, but if we go back, it's roughly in the same layout to the PCA version. Oh, which was on the... oh no, I think I do it up here, don't I? It's roughly the same layout here. So those clusters that you see distributed away are these clusters here in the t-SNE, and then these big clusters here are somewhat closer together in the t-SNE as well. Now, what's going on in t-SNE is as that perplexity parameter increases, you're getting larger neighborhoods, and larger neighborhoods imply closer to linear. So this is the most nonlinear one. And in the most nonlinear one, you start seeing some of the problems with t-SNE. That you start seeing that it's separating these things into little subclusters. Because what these methods are doing is they're trying to preserve local structure, right? And where local is defined by this perplexity parameter and related to your neighbors, right? So if your perplexity is 5, you're trying to preserve structure in the locality of 5 neighbors together. And if that perplexity parameter is too small, you get these artifacts that are not real subclusters. They're just the model preserving local structure really nicely by splitting everything up really tightly, but losing global structure because it deprioritizes global structure. When the perplexity parameter is higher, up to 50 here, it's starting to get closer to linear. And look how similar in some ways this is to that PCA visualization. And we are getting proper structure. The global structure of these larger clusters is maintained. It's not decomposing into these subclumps. Does that make sense? And that's all because it's based on these notions of graphs and neighbors that come up a lot. There's another method called UMAP that is even more popular now. You'll see it's really widely used across the biological sciences. I'm not talking about it today because I'm still, you know, in some sense, I'm still personally trying to get my head around it because the original paper that describes it just, to me, doesn't make any sense. It goes on about fuzzy clusters or something like this, and it doesn't really justify why it would work. So even though I think the t-SNE explanations are a bit strange, the UMAP explanations are really out there. So again, that's one of the things my PhD student Aditya is working on, is trying to bring those explanations within the framework of the other classes of methods, the spectral methods, the manifold dimensionality reduction methods. Okay, so we're just going to end with some practical tips for when you're doing your sort of visualization. And I would do, you know, do t-SNE, do UMAP, you'll be able to find code for it, do PCA, right? But always do PCA first, right? Always do PCA first. And always do these plots where you're going across the dimensions so that you can see under which dimensions it's separating. Because it doesn't always separate data if it has labels, by the way. So if it has labels, include them and look to see that structure is maintained. If you're a domain expert, you might know why these things are clustering, right? You might expect them to cluster in some funny way, right? And therefore, you should be looking for that cluster in the structure, right? So when you're looking at house prices or things like this, you might have instincts about how the data should look. And you're trying to validate those instincts when you look at the visualization. If you don't see that there, one of 2 things is wrong. Either the visualization is wrong, there's some error there, or there's some error in your intuition And that needs to be resolved, right? That's part of being a data scientist, to resolve that. So that's the quick sanity check as well. The PCA is giving you that sanity check, and it's providing a baseline visualization that we could then look at t-SNE further down the line, because PCA is preserving global structure, right? So that's why we could see the perplexity of 50 was looking a bit better for t-SNE. So learn to read gram matrices. So remember we talked about last time the notion of a gram matrix where we're looking at distances between data. So again, I'll go back to the, oh, I've got up here, don't I? To the lab. So there's the t-SNE. And here's a gram matrix representation. Now, it's not very clear what's going on in this gram matrix representation because the data isn't sorted according to the label. But what we would like to be going on in this gram matrix representation is to see the structure that we expect to be in these labels here, in this interpoint distance matrix, right? So what we're doing here is creating this gram matrix, which is the inner product of the data matrix. And then we're just plotting that gram matrix on the left-hand side here because it's a sort of as an image. And then on the right-hand side, I'm just showing you the scatter plot from the oil data again. Okay, but the interesting thing here, and it's a bit hard to see, is that there is structure inside this gram matrix. So where the structure, where things are high, that means points are close together. Where they're low, it means points are far apart. And when you see it in this banded form, what's going on is that there's clustering going on, right? So there's clustering between the points that are high here. So this point is close to this point, is close to this point, is close to this point. So if this data was ordered in the clusters, what you would actually see is a set of blocks in the image. Now, you can't see that set of blocks in the image directly because it's not ordered in that way. There's a reordering of this that would give you those blocks. If this gram matrix is dominated along the diagonal, you can see a bit of diagonal here. I don't know if you squint a bit. Can you see a little bit of diagonal? That's implying there's noise in the data. Diagonal domination implies that there's noise in the data. And then another thing you get, if the data was time ordered, so let's see if we can, sorry, if I can risk something, risk a live innovation on the lecture. What was it called? OSU Run 1 was the other data set. So that was a time series data set. All the way up here. Let's try this. I'm sure this will break for some reason. But we can try and do the gram matrix from at least the gram matrix bit. From that thing, which is a time series, we should see a very different structure. So I'm going to pop that in there and then make sure that we're computing the gram matrix from Y. Get rid of all the stuff that won't work, which I think includes all this stuff. Oh, maybe that will work. Let's try it. Let's just try that first. Oh, do I wish to download the data? Yes, please. So this is the motion capture data. Ah. Oh, where's that? I know how to fix that. Oh, grid spec is not defined. Was there an import? Did I kill the import? Okay. Must be up here. Here we go. Okay, look. Beautiful. You can immediately see this structure, that what's going on. If there's some sort of clustering going on, this is the start piece. But look at this. This is the periodicity. Now it's really clear because it's ordered according to time, right? So what's going on is you're seeing similarities here between neighboring points in time, but then you're also seeing similarities between the points going around like that, because at lots of points in time I'm seeing forward, right? So you're seeing structure in that data. By the way, another interpretation of PCA is what is the best low rank reconstruction of this matrix? That's another interpretation of PCA. So if I want to create this matrix with a low rank matrix, not the full data, what's the best two-dimensional reconstruction will give me the first two principal components. So lots of cool interpretations of PCA. So getting to know Gram matrices is a really interesting way of looking at data. And yeah, multiple 2D views. So that's that thing I was showing you where you've got the sort of scatter plot where you do all plots one against the other. That's always useful. And always examine suspicious patterns. People are just like, oh, there's some weird pattern in there. Okay, let me get on with implementing the neural network, right? No, stop, wait, understand. If there's a pattern you don't understand in the data, something that looks unusual, again, there's either something funny in the data or there's something funny in your understanding. And resolving those two gives you a better understanding of the data. So if you're doing the nearest neighbor thing, then there's lots of little things that you should also be checking. We didn't go into too much of the details of that, but that's this advice is when you're doing those neighborhood methods, right? And you're deciding how things interconnect. Because if they make the neighborhood too large or too small, those methods go wrong in that way. So it's very sensitive to that. Okay, and then very common pitfalls is sort of all of this is very sensitive to scaling of features. If, for example, I take a data set and then I take dimension 1 of the data set and I multiply it by 100, that will dominate all the principal components, right? Because I've just increased one of the dimensions. And so very often, as well as looking at the data set in its original form, people will rescale each dimension such that its variance is 1 or something like that, and look at that visualization. So you do a data normalization in the scale of each column and visualize in that way as well. That's another common thing. Using the wrong distance metric, we haven't talked about classical multidimensional scaling, so less relevant to what we're talking about today. And trusting a singular visualization. Don't ever trust a single visualization. You need to look at multiple visualizations. It's all about bringing your intuitions, and in some ways, it's very qualitative. There are quantitative measures, but in some ways, it's very qualitative for visualization. And often things are not linear. Okay, so I think we'll end there because we're at time. But I mean, I do think visualization is quite hard to teach, so hopefully you've got a sense of it. But it's a lot of fun to do, and I think it's really informative with your data. And I think it often is making the difference between wise decisions in data analysis and foolish decisions. So when you are doing your labs and everything, or your projects, spend a little bit more time on visualization than you would expect to, than you would instinctively want to, because it's a lot allows you to tell the story about why you've chosen to build your model in that way, which visualization you saw. And don't forget to include the different visualizations you tried, right? So that you're demonstrating your thought process, how you ended up with that thing. And it's fine if it's just PCA, at the end of the day. It very often will be, but you can also try things like t-SNE and UMAP or hierarchical clustering as well, just to see what you get, and that Gram matrix to see if you're getting anything out of that. It's, these are like multiple tools to analyze a complex problem, right? Data science is debugging. It's not that any one of these gives you all the answers, but trying multiple of them will help. Okay, brilliant. So we'll stop there.